Welcome to All the Best, an interview series with UNL ORCA awardees, where UNL means University of Nebraska-Lincoln, and ORCA is the Outstanding Research and Creativities Award, which is UNL's top award. In Gerda Lerner's book, Why History Matters, she explains the life stories give meaning to the present and the future because we identify what is important to us. And she says, our stories show how we are interconnected in a particular time and place. As for this interview series, ORCA awardees have experiences that reach back more than a half a century, which will give us a personal view of how the best research emerged from UNL. It is my pleasure to introduce today's interviewee, Emeritus Professor Reuben Rieke. He was awarded the ORCA in 1995. After I provide a quick summary of his life and career, Reuben will tell us about his time at UNL, starting with his award-winning research. Reuben was born in Lucan, Minnesota. Something in his youth must have sparked an interest in science because he traveled 100 miles east to the University of Minnesota, where he earned a bachelor's in chemistry. Next, he earned a doctorate from the University of Wisconsin and did postdoctoral work at the University of California, Los Angeles. In 1977, after about 11 years as a professor in the chemistry department at the University of North Carolina, he joined UNL as a professor of chemistry. I'll share two remarkable facts about Reuben before we get into the interview. One is that his lab found a way to make highly reactive metal halides, now called Rieke Metals, that are useful in many synthetic reactions. The other fact is that Reuben started his own company in 1991 to produce Rieke Metals. He retired in 2004 to devote his full time to running his company. With that, I want to welcome Reuben to the interview.
Thank you, Mark.
So let's jump right into your award-winning research. Give us a sense of how that came about, what it actually is, and why it's important.
Well, actually, it happened while I was a professor at the University of North Carolina in Chapel Hill. And my my early research, we were doing basically involved in about two things. One was no one had really looked at the photochemistry of solid organic materials. They had looked at the photochemistry of materials in solution, but never with crystalline organic molecules. And so we discovered how if you had the right crystalline structure, so it was just a very few molecules that underwent photochemical reactions. And we discovered and explained how the crystalline structure had to be of a certain type before it would react photochemically. The other thing was that when I wrote my first grant, while I was still a postdoc at UCLA, it was to make radical anions, in other words, an organic molecule with one extra electron, so it was a negatively charged material, but it was with an odd number of electrons. And so what you could do with those materials is you could determine and study their EPR or ESR. In those days, there were lots of new chemical pieces of equipment that were being discovered, and that was because of the development of solid state electronics. And so another one of our first areas of study was we were making radical anions, determining their ESR, which is too hard to discuss. Anyway, you make the radical anions. The electron interacts with the protons of the molecule, and from the EPR ESR spectrum that you got, you could relate things like where the electron density was and all sorts of things. And so what we did is we were making radical anions of a lot of organic materials, and then we would examine their structure, and a number of them we were able to do quantum mechanical calculations, so we could relate their ESR to the quantum mechanical calculations that we were doing, and this gave us a way of of understanding the properties of that organic molecule. And so one of the one of the molecules that was it, oh, it was really a hot molecule, and everybody was trying to make it, was cyclobutadiene. And that's a four-membered ring with two double bonds. And every organic chemist was trying to make that. So we had an idea that we could make that not as the neutral cyclobutadiene, but we thought we had a way that we could make the cyclobutadiene, then put an extra electron in it right away and make the radical anion of cyclobutadiene. And then we were going to do the ESR of it, and then we were going to be able to do quantum mechanical calculations to really understand this molecule, which had been so popular. Well, we tried a number of ways, it didn't work. And then we had one new way that we were trying. And instead of getting what we wanted, we got a black mess. Of course, we were not interested. We were not interested in a black mess, but nonetheless, so we kept on our work on the cyclobutadiene radical on it. And we just sort of left it. Other things sat there, but I kept thinking about it. And a few months later, I think I understood what we had made. So we went back and looked at it, and we felt that what we had made was very finely divided magnesium. And so we thought that this magnesium might have special properties, and magnesium was known, had been introduced by Grignard, the name of the chemist, and it's basically where you take an organic molecule with a halogen like iodine, bromine, chlorine, fluorine, and then you insert the magnesium metal into the carbon halogen bond, and you made what's called an organometallic. So in other words, you had an organic portion, you had a metal, and then you had a halogen. And the metal basically is a carrier, and it carries the organic portion to whatever you want to couple it with. And so you can make millions of new molecules by using this approach. The only problem with making Grignards was that it only really worked for iodine and bromine, and a few chlorides would work. And so it was limited in that sense, and for a lot of organic molecules, the only thing that was available was the chloride. Now, the fluoride was even much harder to make, and as a matter of fact, there really weren't any Grignards or any magnesium molecules, Grignards, made from organic fluorides. And so some of these people that have tried to make it, they reacted in a pressure bomb for weeks and weeks with no reaction whatsoever. So the first thing we did was we took this, what we considered to be black magnesium powder, and we tested it, and sure enough, it was incredibly reactive. We could take organic chlorides and have them react rapidly in just a few minutes and make the organomagnesium chloride. And then we even tried it on fluorides. And we were to make organomagnesium fluorides for the first time very rapidly, and we could make all sorts of them, which had never been done before. But the main thing is there were hundreds, if not thousands, of organic, even bromides and chlorides that could never be made. And so we were able to react them with this active magnesium to make these magnesium chlorides and fluorides. Now, the pharmaceutical industry was extremely interested in these materials because they could take these materials and have the magnesium transfer the organic portion to other organic portions, couple them together, and make new molecules, which they would then use in their studies to check their properties as potential drugs. And so they made hundreds thousands, perhaps even millions of new molecules that they could do in their studies for new drugs. And so that was the start of our active metal chemistry. That these metals were far more reactive than any other form of this metal that had ever been studied before. And so we uh, we then tried this approach on a number of other metals. The one that was probably the most interesting and important was zinc. So we could take, I mean, zinc was a hard one to form an organozinc. And so this had been limited to iodides and bromides, which are very hard to make, and there's not a lot of them. So we could take our active zinc. We made the active zinc by the same procedure. We got finely divided black zinc, and it would insert the zinc atom into the organo zinc halide, and we could do that with iodides, bromides, chlorides, and even fluorides. The chlorides and fluorides had never ever been made before, and the organo group for many, many, many different types. They had never been made before. And so, once again, we could take this and make new molecules that had never been made before. And the pharmaceutical industry was extremely interested by this. And frankly, as we get further along in this story, that is what the that was what our company was based on, the active metals, making new organometallic materials, which sometimes the pharmaceutical industry bought these organometallic materials in solution and to make new molecules. Sometimes they had us make them themselves, and so this was the foundation of our company, was the the ability to make all sorts of new either organometallic materials which they used to make new molecules, or else we made them ourselves and sold these molecules ourselves. So anyway, so we started this at Chapel Hill, and by the way, when we left 10 years after I'd been there, I was a full professor.
Okay.
So they didn't throw me out. So I was a full professor there, and they did everything they could to try to get me to stay. But anyway, since I was from southern Minnesota, and actually, well, we'll get to another part of the story. My wife is from New York City, and so anyway, I wanted to come.
Go back to the black powder?
Yes.
You first did the cyclobutadiene radical. You got the black powder. Did you think it was tar?
No.
You thought it was just something going awry?
Yeah, we just thought that the experiment was a complete flop.
Yeah.
We had no idea what it was. So at first, it's just something that I would sit and think about and try to figure out. And actually, I solved a lot of my problems when I used to wake up in the morning about 3, 4 in the morning.
Looking at Loretta here.
Oh, this is true. This is true. And I used to solve a high percent of all my problems. I solved at about 3, 4, or 5 in the morning, and I would think about these things. And so when it came to the active metals, I mean, I used to think about them for weeks and had no idea what it was or what we were making. And then I finally decided that, wow, what this probably is finely divided magnesium. And the reason it's black is not because the material is black, it's because it's very rough surface And so light would come in, strike the surface, and the light ray would get trapped inside this rough surface. And so there was no light reflected back. And that's why they looked like they were black. And so,
Are all the Rieke metals the same black?
yeah, they're all black.
Okay.
And so the same story. They're all very finely divided. They have a very high surface area, and but they all appear totally black, just about all of them. I don't know if there's anything that's not. And but the
Cobalt.
Oh yeah, it's black too.
It's black
Yeah, we did make very reactive cobalt, and we were able to make cobalt carbonyls under conditions that were really, really fine. And see, that's where I guess I got myself sort of in trouble, so to speak, with awards and things like that, because I worked on, I just wanted to do chemistry.
Sure.
And so I gave gave a talk in ETH in Switzerland, and there was a fellow from Purdue who was on leave there, and so I gave my talk, and I talked about magnesium, zinc, cobalt, indium. I mean, you name it, just about every metal we touched on the periodic chart, we were able to make active metals. So this guy came up to me, talked to me after my talk. He says, "Well, Reuben," he says, you're not going to get any awards for this." He said, "Because you're covering too many things." So
Not leaving anything for anybody
yeah,
else.
he said you should just concentrate on magnesium and zinc because and then you'll get some awards from the organic group. And so yeah, so over the years there were guys from the inorganic group would come up and ask me, "Are you an inorganic chemist?" And I'd say no. I'm an organic chemist. And then organic chemists would come up and say, "Are you an inorganic chemist?" So they couldn't understand why, but I just wanted to do new things. And we had a new procedure, and we would make these metals, and we could do things that were in the literature that had never been done before, and they couldn't do them with the metals. And in fact, when I'd write a grant, a lot of the the people that were running the grant, they would come and talk to me, and they said, "Well, now come on, magnesium is magnesium, zinc is zinc, cobalt is cobalt. You don't have anything new. How can you say you got something new?" And I used to say, well, look these are new. They're not just the metals. And so, I mean, we're making them in a atmosphere with no oxygen. We're making them under non-adiabatic conditions, which means these metals did not have a chance to crystallize under normal conditions, so they could grow to a normal crystal, and they had very high surface areas, and so they're just not normal metals, and they have the reaction. Well, anyway, so that used to happen a lot.
Yeah.
And so anyway,
could I also ask how hard they are to make? I mean, can someone practiced in the art also make them in their own lab?
They can. The only trouble is most of the people are very afraid of them. They are, well, there's different ones that are very dangerous and some that are not. For example, you can make active magnesium. I mean, they're all very finely divided. So you can take a syringe and pull it up in a syringe, and then if you squirt that into a hood, boy, you get it looks like the exhaust from a rocket. It's just like that. On the other hand, when you make active magnesium, we could have a bottle of it here, and I could pour it on the table, and it would just be nothing would happen, and it would slowly react with the oxygen and the moisture in the air, and so in other words, some of the metals were really, really reactive. And so, but of course, the people immediately interpreted that to mean all the metals were like that. And so, so nobody really wanted to use them, because they were afraid of that. And but the positive thing of that was when you do something new and it's really exciting, suddenly you got the whole world trying to do it. And so our active metals scared off everybody, so to speak. And so we had this area of research my whole career, whereas most people, when they come up with something new, then suddenly the whole world wants to do it and expand on it. But we had this area of research for our group, basically. Uh, it was just our chemistry, and we could do what we wanted to and do it slowly. And so that was a nice thing about this. But you had to be extremely careful because you didn't the first time you made it, and then after you made it, we would do things. We would take a little bit of it out in the hood and put it out in the to test it and see how reactive it was. But it was. It was something, and then a lot of people, but it is difficult to make. You have to have ultra pure argon, and so you have to have the right. When we had our company, I designed our own hood. I designed our own equipment, and we had our own everything made special for us, and so that was so a lot of people just really couldn't make them. So that's why kind of it just was kind of our thing, so to speak.
So then what type of molecules did your lab make?
Well, we made, of course, with magnesium, we made all sorts of new Grignards. And that was a very, very important thing that pharmaceutical houses around the world. Now, we sold to mainly pharmaceutical houses, but they were around the world. We sold to pharmaceutical houses in Japan, China, all over America. But probably, probably one of the most exciting a new molecule we made was with active zinc. Now, uh, there had been, on paper at least, plastics. Well, plastics are they're just super uh, insulators, lots of things, and they used to have a lot of copper wires were covered with plastics. But on paper at least, there was an idea that if you made a certain plastic, that it actually would be able to conduct electricity, but nobody could make it. So it was just an idea, so to speak. So we had an idea that we could make this with our active zinc, and we did. We made it, and so it was, it was a very, very exciting thing. We published it in Jack's, and it got a tremendous amount of attention. But we made a plastic that did conduct electricity.
What sort of year was that?
Well, that was, I see that. I'm surprised that isn't on this list here. But anyway, that was, no, see, I should have looked, I should have brought my book. I was going to bring my book. And another thing I was going to bring, but anyway, well, I'll explain what that was. Anyway, that was about probably, that was after we had our company. So,
Great.
In the 90s.
I didn't do it in the company, but I did it
Right,
at
timing exactly.
at UNL.
1991.
So it was probably in the 1990s. And but anyway, but more importantly than that, this polymer not only did it conduct electricity, but a major thing about it was if you shined light on it, it created electricity.
Mhm.
So it was a photovoltaic material. And so that was really something that was really, really exciting. So you could take this material, and there were lots of uses for it at first, but after we published that, of course, with tremendous interest around the world and other people making photovoltaics. And of course, you know, you have enough people working on it, like making a new mousetrap. Somebody's, and so several people did make these materials, but anyway, uh, so uh, among other things that we showed that could do is and things that were it used for was like, and I was going to bring that, but I didn't, forgot to bring it. I have a briefcase in which the briefcase on one side has our polymers. Yeah, it was, yes. I wish I could have, I was going to make sure that I didn't forget it, and of course I forgot it.
If you could send
But
me a photo of it, I could put it on with the podcast. People can see it.
okay. Anyway, so you could go to a meeting, and of course, at first, in those days, this was, maybe 25, 30 years ago, when cell phones and things like that were brand new. So the batteries were not very good. And it wasn't like you walk into an airport and wherever you sit down, there's a jack,
Right.
to charge up your. So, you could go to a meeting, plug your cell phone and go to your meeting and then pull it out and you had your cell phone all charged up. And so and nowadays and I'm not sure if they're using our polymer or not. That was made by a company. I doubt that they're still around or that they would be doing that, because now all these things have, like cell phones. They have much bigger batteries, and they have every place you go, you can plug it in and recharge it and all that kind of stuff. But anyway, if you now, lots of places you drive in the country where there is no electricity, you'll find stop signs that have lights on. And there's no, obviously there's no place to plug in. So what happens is during the day, the photovoltaic material generates electricity, charge up a battery. Then as soon as the sun goes down, and at night when you need your stop sign lit up, the batteries turn on. But because every day they recharge, it continues to do that. And another thing is, and we had one of these ourselves. If you have a boat lift and the awning over it, you put photovoltaic material on the awning, then during the day and when you're not there, the photovoltaic material generates electricity. You have maybe a 6-volt battery in your underneath your awning that charges that up. So when you come to use your boat, the battery is all charged, and the battery, and you have a motor that the motor can lower your boat, or when you're done fishing, it comes in there and raises your boat, and your battery is always charged. And so uses like that, this material, whether it's our material or something similar to it, and so anyway, these photovoltaic materials are really very valuable for a number of things, and I think they're going to be increasingly used. At first, we sold a lot of that. Our company still sells it, and so that was really an exciting thing to develop. And of course, the active metals are very important, and they're used in pharmaceutical. And my colleague David Berkowitz has more than once bought. Well, actually, we just gave them to him. some of our active magnesium because he had materials that he could not make a Grignard of, but he could with our active magnesium. And there's a so anyway. So anyway, that probably was the most exciting single material, and so it was when we made it. There were a number of groups that were trying to solve this problem, and they were, so should we say, in the chemical world, they were some of the big shots, so to speak. And when I sent uh, my my oh gosh, what was in the jacks anyway, so when I sent my first paper, and that was when you sent in a short little note, I forget, I can't remember the name now, but anyway, these guys that were trying to make this, and actually, I could have sent it even in a year or two because when we first discovered that, of course, the university wanted to patent it right away, of course. And so we did. We went to the patent attorneys in Minneapolis, and they said, well, now don't publish this. We want to keep this quiet. So frankly, I didn't. I'm sorry now I didn't publish it right away because I would have been ahead of these guys by over maybe a year or two. Instead, I was only ahead of them by, say, a few months. And they were so upset that they went to Jack's editor and demanded that this chemistry be sent out for extra reviews. But nobody else did. Nobody else did that, but they did that to me. And so they sent this to, I'm not sure how many extra chemists to have it be reviewed that it was new and real and had nothing to do with their chemistry, that I didn't copy them by somehow, which of course I had not, because I used active zinc. No, and they didn't know how to make active zinc. So anyway,
So this gets into science being cooperative and competitive.
Oh,
You haven't found the cooperative part.
No, I wouldn't call that cooperative at all. No, it was very competitive.
Well, it's cooperative in the sense that other people review your work.
Well, that's how they want to make it. Sure, it's real and it's important and that it's
but it's something we do as scientists for other scientists, right?
Yeah. So anyway, so that was quite an experience because I was really upset why they would take my papers and send them out instead of three reviewers. They sent them out to 4, maybe 5 people to review it. And
I'm sure you've heard the phrase extraordinary claims require extraordinary evidence.
Well, yeah, anyway,
you have now been validated.
I suppose.
Completely validated by
I suppose, but
the big shots.
So that was probably the most exciting, important thing. Of course, it was really exciting when we first did this, and we could take organic fluorides, and so we had people like E.J. Corey at Harvard, who was ultimately a Nobel laureate, and so he thought that this was really significant, and he was in charge of. I should have brought my Vita along, but anyway, he was in charge of some award, and so he made sure I got that award for my magnesium work, and so anyway.
Well, do you want to move on to your graduate students, postdocs, visiting professors, and just tell us about a few of them, 1 or 2 of them, and then what were their projects and their careers?
Well, I had a postdoc by the name of Alberto Guijarro from Alicante, Spain, and he worked with me for about 3 years, much longer than ordinary. And Albert was a really good friend of ours and did really very, very good work with me, and we published some very fine work together. And so one of the things that Loretta and I have done is we have created or generated a lectureship. You well know about that,
Mhm.
Mark. And so the agreement is that we picked the first three speakers, and so we picked George Whitesides from Harvard as the first one.
He gave a great talk. I loved his talk.
Yeah, and Harry Gray was the second one from Caltech.
Another unbelievable choice.
Yeah, and the third one was we felt we would never have it, and it was totally justified. But we invited uh, Alberto Guijar from Alicante, Spain, to be our third speaker, and so we had Albert come, and so he was our third speaker, and he's a professor at the University of Alicante, and so he gave a very nice talk, and that was a wonderful thing to have him come. So I've had most of my students have gone on to work in industry. I had one of my students became a professor of chemistry at Ole Miss, I guess Mississippi State. I think that's the football name for them. But I think maybe that was I don't know if I had a. Oh no, I did. I had Greg Ebers was also got a PhD with me, and he was a professor at Buffalo State in Buffalo, not the University of Buffalo, but Buffalo State. And I think he might be retired now. It gets a little frightening when all your students are retiring. Makes you feel, hey, how old am I getting to be? But anyway, so Greg Ebert. So I had about two students that taught in universities or colleges, but I think all the rest of them worked in industry, and so. But
So then you told us about your most amazing unexpected finding, right? The cyclobutadiene radical turning black. But was there another one? Other surprising research findings that led you in new directions?
No, because that was the big one. Because at that time, everybody in my group was doing solid state photochemistry or doing ESR work, making radical ions, radical cations. And to further study them, we did a lot of electrochemistry where you would do electrochemical analysis on these molecules. And of course, we were in Chapel Hill at that time, and so Chapel Hill was a center, basically, should I say, of the analytical chemistry in the country, and they were well known for their analytical electrochemistry, and just about every one of their students, I was on their committees because they didn't know really anything about organic molecules, but I knew electrochemistry, I knew radical anion chemistry, radical cation chemistry, so they wanted me on all their committees so I could work with their students, which I could, but of course, I didn't understand the intricacies of electrochemical instrumentation and all that kind of stuff. Even though I did give a talk at one of the Gordon conferences out in Santa Barbara. I don't know. They made a mistake inviting me, but anyway. So
then I showed you earlier your two most cited papers. And the reason I'm bringing these in here is one way that we evaluate quality of science is how many people cite you, right? They've found your work valuable. But it often happens that your most cited papers are not the ones that you would have chosen. So let me just read the title of one of these. Magnetic Properties of Nanostructured Materials from 1996 has over 1,500 citations, which in my personal opinion is a very, very, very large number. You've also got regio-controlled synthesis of poly-3-alkyl thiophene mediated by Rieke zinc
See,
from
that's the
1995.
conducting,
That's the one. Oh,
that's
okay.
the conducting plastics, and that I would expect. But to be honest, this uh, Leslie, she was a physicist,
I know.
and so we worked together, but it wasn't.
Must have been an analysis of the material, right?
Yeah, we did. Yeah, she did some work on that. She didn't stay at UNL here very long, and then she. But anyway, I would have never guessed that that paper would get that kind of. I mean, there must be an awful lot of physicists that were really interested in our active metals and maybe did studies on them. I I am absolutely shocked because I don't keep track
Yeah.
of citations, and I never have.
I just wonder, so with the burst in interest in quantum materials, right? So this is magnetic properties of nanostructured materials.
Yeah,
There's a quantum angle to it.
yeah,
It could be that this is providing people with ideas.
yeah.
Just what I was thinking.
Well, anyway, I'm very pleased. I mean, I like to work with her, and she left, UNL several years ago, but I'm
And then
very.
I tried to find the original Rieke Metal publication, and you can see here, 1972, Activated Metals 1. Was that the first paper?
Yeah, that was with Phil Hudnall. He lives in Tennessee, and we communicate with him. We get each other letters every Christmas, and he's from West Virginia, and he was a tough guy. Should I say from West Virginia? He used to talk about how tough their high school football games were, and how I mean, it used to tell me how all these uh, feds, the Fed guys used to go up in the mountains to look for the moonshiners, and many of them never came back. Anyway, that you can take off.
Yeah. But this one, if I recall, I should have written down how many citations it had, but let's say it was like 500, which is again, a super large number, but it's not 1,500. Why do you
I
suppose this
don't
is
understand that. Well, maybe that's because the should we say, I hate to refer to them as that the superstars came out with a publication, but their conducting plastic was not as good as ours, and it came out probably 2-3 months after ours, and so maybe they're the I don't know. I can't tell you that, Mark. All I know is that would have. I mean, I would have thought that Phil's paper with me on that was the first paper of our highly reactive metals would have been number one. Although the plastic, the conducting plastic, the photovoltaic material was an exceedingly important discovery, and so.
But then tell me about editorships, patent applications, companies that you started, books. There's a lot of stuff.
Well,
I got this earliest patent on here. You've got 22 patents.
well, I think that should be. I'm almost positive we had 25, but
Okay.
that's not too critical. But well, the thing is, when I first started getting into something that was patentable, they didn't have a patent committee at UNL like they do now. Okay. And so I think they only had one guy. He was a engineer, not picking on him. But anyway, I remember going over to his place with our first paper on active zinc. And that was a barn burner. That would have been I'm talking about a really big patent. And he looked at that paper and he said, "No, I don't think that's worth anything. We're not patenting it." Now, what could I say? I couldn't say anything. So I just went back and we published it and all that kind of stuff. But no, he was an engineer, so he didn't know any organic chemistry, but that was just a monumental mistake by the university because that active zinc because we made a lot of active zinc in our company, and we made all kinds of organo zincs, and they were in that paper. That means that you could make them. So anything that was made by them, we sold the active zinc to companies. We sold active zinc to Aldridge. They sold it for years, and no, that would have been an absolutely monumental patent. Now, the active magnesium, that was made when we were still in Carolina, so that was too late for that. So
maybe those are the patent applications that I didn't get. I think I only captured the ones from Nebraska.
yeah, well,
So, how hard is it to write a patent application?
that's a real that's a difficult thing. Now, we of course had a company in Minneapolis, and they of course wrote it and all this kind of stuff, but I mean, we had to help them. I had to help them, and so that was no writing patents and getting patents issued. That's a challenging job. But like I said, I think we had 25 patents that we had issued. I don't know, probably I wrote and we submitted another, at least 5, maybe more. So probably tried to get about 30, 35 patents over my career.
So how about editorships? Did you do much of that?
No, I didn't. I just was interested in doing chemistry. I never got into that. And
Did you write any books?
yes, I wrote 2 books. One is, and I should have brought that. It's a book published by John Wiley and Sons. All my career, every time I would go to an ACS meeting, I knew this one guy. We used to go and look at new books, and this one guy used to, every time that I would go to an ACS meeting, which Rudd and I went to a lot of them, he would always say, "I want you to write a book on your active metals." And I would just say, "I don't have the time to do that, And so when it finally retired, that's when we had the time. Loretta helped me a lot because she always typed. I couldn't type. I don't know how to type. She always typed up. I would write out the pages. She would type them. And we had one other big helper, and that was our cat Buddy. Because I could not sit down and start writing without Buddy coming and laying on my arm. So I have to give Buddy credit too. So no, I wrote that book, and it's been published, and we it was quite interesting when we were ready to publish it. Wiley's called us up and they said, "Well, we don't do indexes. Do you want an index for your book?" Well, I never published a book in my life. So I said, "Well, I don't know. Do you think we should have one?" So he said, "We have a deal with a company in India, and they will do the indexing for you, and they will take your royalties until they paid their bill, And so I don't know how many years it is now, but this Christmas we got a letter from Wiley, and what should be in that letter but a check for $138, the first royalty check in all these years. So the bill from India must have been humongous. So anyway,
that's one book.
That's one book. Well, the second book is not chemistry. My ancestors, my great-grandfather, my great-grandmother, and my other great-grandfather came to Minnesota in about 1850, and they settled there and started farming, and the counties that they were in were basically nobody was there. It was empty. And so they
What's the name of the counties?
Renville County. Okay. And so anyway, so when the Sioux uprising started in September of 1862. Uh, they had become very, very close with the Sioux Indians. They all spoke Sioux, and so anyway, so they would anyway. It's that story called "Fire in the North." Is written by me I don't know if you remember Tom Phillips. He worked for the department. Well, he is a military historian. And so I knew I couldn't do this all by myself because I'm just not a writer. But anyway, so I finally got Tom to agree that we would write this book together. I would basically provide all the material about the settlers because I had newspaper paper articles from way back when. I had letters from my great granddad who wrote my ancestor settled in southern Ohio at first, and then it wasn't until the uh, the uh, the Sioux and the white people call them that. I don't know what else. Or
Settlers.
well, no, because they were the politicians in St. Paul,
I see.
and of course they totally took advantage, and so anyway, that's when they opened up southern Minnesota for settling. And so my ancestors, they didn't want to go south where there's trouble. The trouble with the Civil War hadn't started yet, but it was on the verge. Anyway, so they came to southern Minnesota and very close to Fairfax. That's why we lived in Fairfax. And so
So then how about your company? What sparked you to want to start your company?
well, because I knew from just experience that my chemistry was not, it was going to be buried. Okay. It was going to be in the library and somebody would look up every 100 years. Not that bad. So I knew that the only way it was going to, in the chemistry, the molecules you could make, the conducting polymers, all this was going to be just buried unless we put it out on the market. So Loretta and I, we that was when Henry Baumgarten, Henry, or anyway, that's when the patent part of the university was growing, and so we went to Henry and we said, okay, Henry, we would like to start a company, and so we told Henry, we don't want any trouble, okay. So we told Henry, you write up a contract, we'll sign it. And so we started. In those days you could lease some of your own labs, and so we leased some of our labs. I would buy out about 25, maybe 30, 40% of my time. And so then I spent that working in our company, which was right in my labs. It was right across the hall. And so
I remember.
yeah. So that's how we started. And so, and eventually, we were able to save up enough money that, I don't know if you've ever driven out there and seen her, but yeah.
I brought summer research group there, I think 2 different summers.
Yeah, that's right. Anyway, so when we sold out finally, because we figured we're getting so old that nobody's going to buy it because it's very tough chemistry.
Yeah, I know.
Yeah. So anyway,
But it's still going strong, right?
well, we told everybody that looked at it, there's 2 requirements. One, it has to stay in Lincoln, which of course any big company would not want to do that. But we felt this was important. So we wanted to stay in Lincoln, and that we wanted the people in our company to stay in the company. And so we finally got someone from Raleigh, North Carolina, to buy it, and it's still there today. It's still doing well, And I guess, is there anything else we need to say about that, Loretta?
Mainly the same people. Some have retired.
Oh.
So anyway,
It's been a very long time.
that's but it no, a lot of people, like everybody, Phil called me in and said, "Don't do that.
Oh.
You're gonna have problems. It's not gonna work."
Yeah.
So I had people call me from around the country that I didn't even know. It's true. And they said, "Don't try to do this. It's not gonna work. You're gonna, and no, I mean,
You did fantastic, right?
we wanted to do it.
Yeah.
It's just like, when I left Carolina, my boss at Madison called me up and said, "You better not leave. That if you try to leave, I'm gonna make sure you'll never get a job, even as a even as a dog catcher."
That's terrible.
No, he said that, and I said, "That's what I want to do.
Yeah.
So we're gonna do it." So
So that's great. It's your ancestors' state ability to do what they want. So let's talk about funding. What organizations funded your research, and then how did the funding opportunities change during your career?
Well, yeah, the funding at first, it's kind of interesting. I wrote a grant to NSF. Now, you'd think NSF would be the one that would support it, right?
I would, yes.
They said, "No, we're not supporting you." So the very first place where we got some money, see, I should have brought my Vita because I'm missing some of these names, but there was a an organization that Harry Gray will help run. Okay, all of the all of the oil companies in America gave a bunch of money for a trust, and they
Is
gave
this the
out.
Petroleum Research Fund?
That's right.
Okay.
And so they gave out grants. So my very first money that I got was from that organization. And then after a while, NIH supported my research, and that was, of course, was a big one because they gave out a lot of money. Eventually, NSF,
Eventually.
because none of these people would believe that our metals were different, and they are. And so anyway, and then I got some money another time at the Department of Energy. And so I would say NSF, NIH, Department of Energy were the big supporters of my research. And because at one time I had grants from all three, which was very unusual.
Yeah, that is very good.
So
what techniques and instruments did you use in your research?
Well, after we got to the active metals, really nothing except for making things under high purity argon. We had a glove box, for having. Otherwise, when I was doing my photochemistry, then of course we had a lot of photochemical equipment, specialized photochemical equipment. And then when I was doing the ESR, of course we had to have a special ESR, and at Carolina they had one. They're very expensive, and so
And again, ESR, we mentioned this before, electron spin resonance. Again, it's about the quantum properties of the electron.
well but we did, and of course we had to have a big. I mean, we didn't have that, but the university always had big computers, and so we would do our quantum mechanical calculations in the big computer. So we would use that, and but otherwise, when it was just pure metals work, which eventually had moved to that, and because everybody. It was so funny. I probably shouldn't tell you this, but anyway, once we got the active metals, we got this verified that it was active magnesium, and E.J. Corey got me an award and talked to me about this, and everybody who was doing photochemistry or electrochemistry, they all dropped their projects and they all ran to the walls where the metals were. And everybody was grabbing one and saying, "This one is mine, cobalt's mine, nickel is mine, indium, this is mine." It was so funny. But anyway, and then of course I had a Beckman DU, and so
Sure.
for UVs.
Sure.
But anyway, so that was.
So we've already talked a little bit about science being competitive and cooperative, but was your work ever scooped? I mean, you talked about how it felt as though the forces were trying to prevent you from scooping them, but were they ever scooped?
No, not really, because what we were doing was so unique that
Mhm.
nobody else was doing this, and so we didn't have to worry about that, never did, and so you know. And I know you have a question there about did you ever make a mistake? And
Yeah.
the answer is yes.
Okay.
Yes. And the good thing was that we discovered the mistake before anybody else.
Yeah.
And then we wrote a paper explaining that we had made this mistake. We explained the mistake, which really is a very interesting one. And but anyway, so that was the only mistake we ever made. We caught it ourselves, we published it. So, but anyway, yeah, when we were, well, I don't know if I should explain that or not. Take some time.
Yeah, I know. Let's avoid that. So yeah, that was the corrections, and when you're working fast, sometimes you publish things that are not exactly correct, right? But then you're continuing to work in
Well,
that
it
area.
was such a major,
Oh.
I mean, it was wrong.
Mm.
But the thing was, it was such a major discovery that when we sent it in, it was immediately accepted by JAX and published, and it got if you had the citations,
Right.
if that had been if that had been correct, you'd probably have more citations for that than anything.
I see.
But yeah, we thought we had made benzo cyclobutadiene radical anion. So that's a benzene ring with, a cyclobutadiene ring and then we had a benzene ring onto it.
Mhm.
So that was a benzocyclobutadiene,
Yeah.
and we had thought we had made that. But
Conjugation.
it was what we had made was it was very interesting, very complicated. But anyway, we had made a benzocyclobutene, and this double bond out here was so basic that it pulled off proteins from THF. So these two carbons out here didn't have one hydrogen and flat with a double bond.
Mhm.
They had two hydrogens on it. They were so basic they pulled off two hydrogens. So we had two. So when you do ESR, you can predict the number of lines by just 2n, 2 plus 2n plus 1. Okay. So in other words, if you had benzocyclobutene, you would have 2, 2, and 2. So it'd be 3 times 3 times 3. That'd be 27 lines, right? So we did the ESR. What did we get? 27 lines. Now, the thing was, what had really happened was instead, we had the benzo 3 times 3, but then we had 4 protons here.
Mhm.
So those 4 protons, they could have been 5, right? So it could have been 3 times 3 times 5. But we didn't find that. We found 27 lines. And what had happened was this radical anion, of course, it's an anion. So we made it from sodium potassium alloy. So there was a sodium ion, and so the sodium ion was sitting on top, okay? So these two protons were different from these two. So it should have been 3 times 3 times 3 times 3, and should have got 81 lines. But we didn't. We got 27. So what was happening? the sodium ion was jumping from the bottom to the top. And so if you if you had a certain time scale of this jumping, you went from three times three, and then the line, the lines out here, the spectrum, it would they would they would spread out. They would spread out. And we just by chance, just by luck, they were jumping at the rate such that these lines had collapsed to just three. I mean, it was just unbelievable. Nobody would have, and we finally figured that out. And so that's how we had 3 times 3 times 3. But it was really due to the fact that we had the sodium ion jumping top to bottom. And then if we went to much colder, much warmer, then we got 2 times 2 times 2 times 2. So we ended up, so we figured that out, crushed our, just felt terrible.
So is this a solid material or a liquid?
Oh, it's in solution.
It's in solution. Okay.
Yeah, it's a single, it's a molecule, and it's in solution. But no, that was a terrible. Well, but the good thing was we caught it ourselves.
Oh, I know. Yeah, that is always good. So yeah, that's the end of the research part. But is there anything else you want to add about the research part before we move on?
No, I think we talked about most everything that's really exciting, and except that we've made dozens of I don't know how many active metals, and every one the only active metal that never worked. This I was going to bring that too. I still have that today. Is that when we tried to make active gold, we made nuggets.
Good for you.
And I have a little vial of gold nuggets to this day.
Gold's going up.
It sure is.
So let's move on to other career activities.
Oh, okay. You wanted to know about what did I do for entertainment?
Oh, yeah, that's at the end.
Pardon. That's I had 2 things that I really enjoyed.
Yep.
When I was away from chemistry, and that was, of course, growing up in Minnesota. I was a very, very active fisherman, and so I love to fish. And then the other thing that I loved to do was to garden. I always had a big garden, so I grew all kinds of vegetables. My wife grew flowers. So she was the flower person. I was the fisherman. And so that were my 2 major items,
So, but I want to talk about other career activities, your youth, and then your undergraduate training. So other career activities would be, what conferences did you go to?
Oh, mainly I went to
ACS.
Yeah, the ACS.
Okay.
I don't. Well, well, there was a very interesting side story, and of course, I was an electrochemist too, but of course, you remember the Fleischmann and Spahn.
Yeah.
Okay, so they. I knew Fleischmann personally.
Oh, wow.
I'd visit him in England, and he'd been to Carolina. And he was a very, very competent electrochemist. I never met Pons. But when Fleischmann said, this is real, well, I believed him, okay? I don't know whatever happened to that. But anyway, is it getting late? I'm taking too much time. Anyway, so when Fleischmann said, this is for real, okay, I took it to be real. I never, ever wanted to try to do what they did, because I never did stuff what other people did. And so, but I thought, what if I took my active metals and made electrodes from those? What would that be? And so, anyway, with the guys down in the shop, we made some some electrodes, and so I did go to a meeting in oh by the in New Mexico by the nuclear.
Oh, the Lawrence, no, not Lawrence,
Well,
National Lab.
yeah, the National Lab. Okay, so they had a big meeting there at that time, and so I mean there were thousands of physicists and electrochemists, and the physicists would get up and say, "Oh, this is a bunch of baloney. It can't be," you know. And the electrochemists would get up and say, "Oh, hey, I did this and got all this heat and all this kind of stuff."
Yeah.
And, you know, well, I didn't. Of course, I didn't open my mouth at all. I just sat there and watched all this. But anyway,
But that would be memorable.
so I had a postdoc, and oh, somebody that was a banker in town, the Stewarts, they called me up to their office. And they said, there'd been a article written by the paper that I was doing work in fusion. Well, really. So they called me up there and said, "Well, we want to give you some money to do the fusion work.
Oh, wow.
But if it works,
Mm.
of course, we want a big cut of it." Because I didn't care about that. I just wanted to do the work in that. And so anyway, my postdoc, we set up a place where you can monitor the heat and all this kind of stuff, 24 hours a day. And so, and we did palladium electrodes and all this kind of stuff. We had D-tool and all that. Anyway, one morning, Kershaw, we came in, and it was a real shocker because our electrode was no more.
Mm.
And then the bottom of our cell was all kinds of small particles. But when we looked at them under a microscope, they looked like droplets, like you would, well, whatever, you have water, you have some. Anyway, they looked like, and the heat thing was we had a that monitored the heat, a tape chart. I have these things where anyway. So that happened when went off the paper.
Oh,
And so I mean, how could that happen? And so when there is a event with palladium has a certain ratio of isotopes. Okay. And I don't know what they are, but there was a natural, there were whatever the natural was. So there was a mass spec guy at University of Illinois. I don't know him anyway, but I was told he could do metals. So I just called him up and said, "Would you like to? We have this palladium. We had this event. Would you check the ratio?" So anyway, we sent him that, and he called back after he had examined it, and the natural ratio, atomic or ratio, was not there. It was different. So I said, "Well, we should publish this?" Well, that was about the time when anybody doing fusion work was considered to be a little.
There's still people doing that,
There probably are. Anyway, so he said, "No, I won't, and I won't give you my data."
Oh.
Yeah, he said, "I don't want." He said, "I don't want to be touched, but I don't." No, that was it. So anyway,
So we could all be using your cheap energy if only.
So that was another interesting, so we took that to the university, and now this was something that this was before Henry and the guys also had a a real big program on patents. But anyway, so now this guy, this was something that was very interesting to him. So we filed a patent.
Oh.
And we got a patent.
Oh.
I
Is that right?
I have a patent on cold fusion.
Oh, wow. I missed that one. I should have.
Don't put that. Don't put that in there. I will be listed as
A crank.
a crank. You bet.
So, what did you do during your sabbaticals, if you took any?
Yes, I
And-
took two.
Oh, you did. Okay.
Or three actually. I went to Stanford once, and I went to Princeton once, and then we went to Munich, Germany. And we were in Munich, Germany for about from September to the following May? So anyway,
And so what did you do in those sabbaticals?
well, basically when I was in Munich, I did active metal work or wrote papers. No, I had nothing to do with that. Just these were guys that I knew. They were friends. And when I was in Munich, when I was in Munich, the reason I ended up there was simply because, we'd never been to Europe in our lives. We didn't know anything about Europe. And I had a friend at Bucknell University. And he was a real close friend of E.O. Fischer in Munich at the Technical University. As it turns out, the year I was there, he got the Nobel.
Oh.
So anyway,
That's
so Ben says, why don't you go to Munich? I said, all I need to do is call up E.O. and you have a position there. So, and I had I won a fellowship from NATO. So I didn't need anybody's money.
Right.
And so we went to Munich. It was quite an experience. We had a lot of problems at times, but we had a wonderful experience there. Got to know some people real well, and they came to work with me. And well, not work with me, but I don't know what Carl and his family came to Chapel Hill. I guess it was Chapel Hill then. Yeah. Anyway, but we had and when we were in Princeton, and basically I just wrote papers there. And when I was at Stanford, I think I wrote papers there. And I never did any research except when I was in Munich, because that's when EO said, why don't you make active chromium? Because nobody can make chromium hexacarbonyl by taking chromium and CO under high pressure. It just doesn't work. So I showed him. That's when I did some work with one of his assistants, and because I didn't have any high pressure equipment and never worked with it. So Carl and we made active chromium, and we put it in a big bomb, and we actually made chromium hexacarbonyl, which is in my book. And so, that's the three sabbaticals I took.
How about teaching? What courses did you teach more often than others, and what are your thoughts about teaching?
Well, I taught, of course, the two undergraduates, 250, 261.
Large enrollment,
Yeah,
non-chemistry
yeah,
major.
down there. And then I also taught the graduate course so I taught all three of those. And when I was in Chapel Hill, I did teach freshman chemistry a couple times.
Wow.
I mean, when I came there, they just said, okay, this is what you have. And in Chapel Hill, when you were starting out, I mean, what breaks do they give them now?
Yeah.
Get
I know.
real big breaks.
They do, yeah.
So when I went to Chapel Hill, the first year, I had 3 courses to teach. Yeah.
Wow.
So I had 3 courses to teach. And my first semester there, I taught freshman chemistry and I taught organic. And in those days, Carolina still had Saturday courses. So I taught 6 days a week. No notes ahead of time. So I taught, and then because I was a beginner, well, Jim Coleman was there at the time,
Oh,
and he was interviewing. So
Oh.
he was going all over. He
Oh.
was gone just about all the time.
mm,
So of course he would say, "Hey, Reuben, would you take my freshman class?" And of course I'm going to say to Jim Coleman, "Oh, Jim, up your nose." So I was giving. I mean, I had 6 lectures a week from my stuff, and then Jim Coleman many times was gone 3 days a week, so I had to give. And then there was and then there was the times when I don't remember who it was, but I was teaching for someone else in the freshman class.
mm.
So sometimes I was giving 10 lectures a week as a beginner.
Wow. So that'll really give you practice.
Well, they worked.
Trial by fire.
Oh, it was. It was. So, every night I was, I was writing a lecture for the next day, sometimes two. And
I think every professor does.
so,
But you had a lot of them to do.
yeah, absolutely. But,
So let's
You
move on
know-
to your youth. Where did you grow up and what was your childhood like?
well, I was born in Lucan at home, and then we moved to Fairfax. And then my dad was managed grain elevators. That was his profession. And so about when I was finished third grade, my dad got another job, um, and he obviously got a pay raise. So we moved to another little town
Mm.
called Denison.
Oh,
And Denison, so that was another town.
Mhm.
And I'm not making this up, but it was another town of 180 people. And so we had, in both of these towns, we had electricity, but no running water.
Mhm.
And in Denison, so since I was now going to be in fourth grade, we had a 2-room schoolhouse. So I went to a 2-room schoolhouse for a couple of years, and so the room I was in, we had fourth, fifth, sixth, and seventh grades, and there were 4 kids in my class, counting me. So we had 4 kids, and the good thing about being in that situation is because I could sit and listen to Mrs. Conley teach science to the 7th graders. So, so how did I get interested in science? It was from Mrs. Conley, and
Mhm.
so anyway, then we went back to Fairfax. I finished graduated there, and then I went to University of Minnesota, where they did have a program. They had, of course, a Bachelor of Arts, Bachelor of Science, but they had this unusual degree, which I'd never heard of any other school having it, and that's the Bachelor of Chemistry.
Oh.
And so that's what I signed up for.
Mhm.
And in orientation, the first day of class, there was 300 of us that were in that program. 4 years later, when we graduated, there were 13.
I also went to Minnesota years after you, but ended up getting a biochemistry degree. But they did tell us on the first day, right? Very few of you are going to get through this whole program.
Did you have a big?
It was a very large class, filled one of the lecture rooms. I don't remember the number, 200 students or something.
Do you know how many graduated?
No, but it was a small number.
Yeah, well, we went from 300 down to 13,
Yeah.
and
So severe.
and then the guy that got to be my really good friend and assistant and assistant, advisor, etc. All my whole life was Dr. Nolan, and I did undergraduate research with him, and I used to work extra hours after class, even though when I was doing work, I would go up to the lab and spend time up there working, and that's where I did a project with him. I mean, it was a research, okay,
Yeah.
and we solved the problem, and he wrote up a paper in JR Chem
Oh,
where they had, I don't know what they called it. It wasn't a full paper, and it wasn't
a letter, communication.
yeah,
something
probably a
like-
letter. And so that was my first publication.
Oh,
I still have a copy of
wow.
that. And so Dr. Nolan was he was and he taught organic chemistry at Minnesota until he was in his 90s.
Wow.
And no, he passed away now just a couple of years ago. And so anyway, so that was my first research project with Dr. Nolan, and ended up in a paper.
And then how about choosing Wisconsin? How did you do that?
Well, I was accepted by several schools, including Harvard, and so it just was. I just didn't have a desire to go there, and so I went to I chose Madison, and that's where
You meant an undergraduate.
she was in the graduate program in organic chemistry.
Okay.
We met and fell in love.
Yeah.
We're still married.
As grad students. Did you marry as grad students?
Pardon?
Did you marry when you were graduate students?
Oh yeah. We got married at the end of the first year, really.
Oh,
Really. Yeah.
quick mover.
Well, she was from New York City, so she was born in Manhattan. And I was born in Lucan, so it's about the same size. So
Her apartment complex, the same size as your town.
so anyway, that's Dr. Nolan said, well, Madison is a very good school. It's got very good people, and actually the person that I went there to work for, just that year had decided he got a position at Stanford, and he was a bioorganic chemist, and that's what I wanted to be. So when I came to Madison, he was in the process of moving to Stanford. So his group was moving and all this kind of stuff. And then when the guy that was signed me up, once again, I got a little loss of memory. But anyway, he said, well, everybody every organic chemist that comes to Madison, they minor in physical chemistry. Well, in those days, it isn't like today. Now, today, I would have said, I'm bringing my lawyer in, right?
But you get to do whatever the program.
Yeah. And so
Today it's more tailored to everybody.
yeah. So anyway, I said, well, okay. And anyway, Van Tamelin was his name, was on the way to go to Stanford. I think I went in and talked to him, and he said, well, look, he said, there's already two people in this program that I had made commitments to before they even came here. They're from Michigan. And so he said, I'm going to let them join my group, but I'm not letting anybody else join my group. So he was a bioorganicer, and then when I was told I had a minor in physical chemistry, and then so I got pretty interested in theoretical. So I took a bunch of courses from Hirschfelder was his name. He was a very prominent theoretical chemist, and so I took a lot of theoretical chemistry from him. And so at one time I was thinking of switching, but that that was a little bit, as they would say, beyond my pay grade.
Yeah.
So
But I think it served you well, right? Because you then
Yeah.
had the whole background.
absolutely. Well, at Wisconsin, you see, you just didn't take courses in your major.
Right.
So I took courses in PChem, I took courses in inorganic chemistry, analytical chemistry. Oh, yeah,
You've brought them all together.
everything was valuable to me because when I was working as an electrochemist, I did all this kind of stuff. I worked as an electrochemist, and I worked as an inorganic. We did inorganic chemistry. Maybe that's why I was able to do all this stuff, and nobody could figure out what kind of chemist I was.
Organic.
Yes, no. I always said I'm an organic chemist, period. Now you guys can call me what you want.
I think whatever you teach is probably more aligned with
Yeah,
what you are called.
yeah.
So then choosing a postdoc, how did you do that?
Well, there's a long story to that too. Anyway, but so no, I applied to several groups and I was accepted by several groups, and so, but the guy I really wanted to work for was at Berkeley, and he was he was a theoretical chemist basically, and since I was interested in theoretical chemistry, he was doing quantum mechanical studies on organic molecules, and so I called him up and I said I really would like to work with you. So he said, look, he said, I have 2 grants which are under review. I have not heard from them. I have this group of postdocs. He said, there's no way I'm going to be able to support anybody else at this point in time. He says, if I get any grant, you're in. So anyway, at UCLA, the guy, Saul Winstein was his name, very famous organic chemist. And the year or two after we left, the word was out. He was going to be the Nobel laureate, but he died of a heart attack. So anyway, as soon as he got my application or my letter, he called me up and said, you're in my group. So I knew he was a very famous chemist, and he was, someone who treats you that way. So so then I got an NIH fellowship, and so I had my own money. I could go wherever I want. So I called Saul up, and he said, or he called me up, and he said, well, now that you got this, he said, you can go wherever you want. I know you want to work for Streitweiser at Berkeley. I said, look, you made a commitment to me, and I'm going to honor that. So that's why I went to UCLA. But it was very good time. He was very good to work for. And then when I got there, he said, you got your own money? He said, you can do whatever you want. So I said, okay. I said, have you ever tried? He was looking at through space interactions, p orbitals that were tipped, and they weren't on the same carbon, but they were tipped, and so he called that through space interaction. So I said, have you ever looked, because I want to do ESR and all that, so I said, have you ever looked at these molecules? And are we behind time? We are, I'm sure. Anyway, so I said, how about making radical anions of these and doing ESR? He said, that sounds great. Go ahead. So that's how. Anyway, so I worked with him. He was a very, very nice guy, and it was fun working for him.
Sounds really good. So in retrospect, how far did your research as a professor diverge from your graduate research or postdoctoral work? How much divergence?
Oh, the thing that I always considered to be absolutely a no-no, because I knew there was lots of guys that I went to school with, and they would go off and take their job and then they would do extensions of what they had been doing. And I thought that was totally wrong. So I would never do that. So that's where I started out with my own ideas, and that's so no, it had no connection with that because I wouldn't do that.
Okay. So then the last section is about personal. Tell us about your family. Did you marry or have a partner and or children?
Pardon?
And or children?
We have two children, one boy and one girl. Our daughter is in town here, and she runs a tea shop just right down where that's where we're going. And we now work with her in the tea shop. So that's my third job. And so and our son is a PA at UNMC in Omaha, but he's also a in the Army National Guard, where he is a colonel, a full colonel, and he is a commander of all the medical units in the state. And he started out by going to Desert Storm. He was in Desert Storm. He was in Bosnia, and he was a flight surgeon in Iraq.
But then in the context of your career, right, you're marrying in Wisconsin, going to LA, and then going to North Carolina and Lincoln. Where were all the children born? This is a test.
Elizabeth was born here.
Oh, she was. Oh.
Yeah, Dennis was in North Carolina. So.
Then we've talked about the other stuff. And since you've retired, how do you spend your time now? We just learned that. So I think we're at the end of the interview. And I want to thank you very much for talking to me today.
Good. Hopefully you got what you want.